All right, so here's the video for the third problem of the WebAssign homework from section 8.3, the one about the swimming pool. And so they give the dimensions of the swimming pool. So they say it's 20 feet wide, 40 feet long. Its bottom is an inclined plane. The shallow end has a depth of 4 feet. So here's the shallow end with its depth of 4 feet. The deep end is 11 feet. It says assume the pool is full of water. Okay, so it's 20 feet wide, so this part's 20 feet and 40 feet long. So I'll do part B and part D, and when you see me do part B, part A should be just like it, and then I'll also talk about part C. So probably the easiest one to start with is B then, if I'm gonna do either A or B. So it says estimate the hydrostatic force on the deep end. So they mean on this face right here. Oops. On this face. And then the shallow end would just be that face right there. So think of if I drew a typical strip on the deep end. Okay, so remember, so this is part B. So force equals MA. And so the mass, so now we're in the English system. So it's not rho V anymore. It's not density times volume. And because I mentioned this in my other discussion posting, if I do this times a volume, which would be in cubic feet, the cubic feet would cancel and my answer would be left in pounds, which is a force, not a mass. So when we did rho V in the English system, we got the weight in pounds, which is also a force. And weight is mass times gravity. And so if I want the mass, I divide both sides by gravity. So M is really rho V over G. And the acceleration is the acceleration due to gravity. So the G's cancel, and we just get rho V. And so we need the strip depth times the strip length, and then times delta Y. So this volume is like the volume of water pressing on it. So the depth, the length, and then there's the part that's experiencing the force, delta Y. For one of these end faces, these end walls are rectangular and the length is always the same. So the length is just always 20. And so our rho was 62.5. The depth, it would just be the surface minus y, and this is 11 feet, so it'd just be 11 minus y. The length is 20, delta y, and now I'll put it all in an integral. So that's the force on this, I should say S, the force for that strip. Okay. And so then the total force, the total hydrostatic force, I'll bring the 62.5 and the 20 out in front. And so all we have left is 11 minus y dy. And those strips are just I'm going to call the bottom 0, are just going from 0 to 11. And so 62, you can do this on your calculator, but 62.5 times 20 is 1250. And then we'd have 11y minus 1/2 y squared. And that's going from 0 to 11. So we just have 11 squared, which is 121, minus 1/2 times 121, minus, and both times we plug in 0, we get 0. And so you can just do this on your calculator. And, oops, I get 75625. And that would be in pounds. Okay. And so then I'll do part D. I think part D is the hardest one, and then I'll talk about part C. All right, there's a lot more to part D than I would ever expect you to do on a test or anything. So let's talk about this. So here I've drawn a picture of, we can think of this as being just the bottom, the floor of the pool. So it's at this incline. The width will always be 20 feet. Okay. And so let's try to figure out the force exerted on this little strip that I've drawn on the floor. So force is always mass times acceleration. But remember, in the English system, when we do rho times V, that's pounds per cubic foot times cubic foot. That would be pounds or a weight. And weight is mass times gravity. So if we want to solve for mass, we divide both sides by g. So m equals rho v over g. So we get rho v over g, and acceleration is the acceleration due to gravity. So the g's cancel. And so force is just rho v. So now I'm going to focus on a strip. So our rho is 62.5. And this volume, we think of the volume of the column of water pressing on the strip. So there's this column going straight up from it. So the length of it, we'll think of length, width, and height. The height of the column is the same as the depth of the strip. How deep it is the height of the water pressing on it. So for now, I'll just write length times width times height. So the height is the same as the strip depth, because that's the height of the column of water. Oops. Okay, so the length is going to be 20. The width here, the width is actually the hard one. We will still have to figure out an equation for the strip depth, but that's not too bad. The width I'll talk about last. So for now, let's do the strip depth. And so I want to get like an equation of this line. Well, I have to decide. So here I'm looking at things happening horizontally. So I'm thinking of going with respect to x. And so I have to decide where to put x equals 0. Well, I think it makes the most sense to put x equals 0 right here, way on the left. So when x equals 0, the depth, or the y, is, well, when we're way at the left end, which would be the deep end of the pool, the depth is 11. And then at the other end, at the shallow end of the pool, is when x equals, well, it's 40 feet long, so then x would be 40. Y equals, well, the depth is 4. So as soon as we have 2 points, we can figure out the equation of the line. So let's get the slope. So m equals y2 minus y1 over x2 minus x1. So we get negative 7 over 40. So there's our m, but if x equals 0, that is the y-intercept. So the y-intercept would just be 11. So y equals negative 7 over 40x plus 11. So that's what I'm using for my strip depth. This will tell me at any point x what the depth of the strip will be. So the width of the strip. So say I were to just sort of zoom in on this. Unfortunately, this width is not delta x. That's not just a horizontal change. So what I'm, sorry. So there's the part of the strip I'm looking at. This would be my delta x. If you wanted, you can think of delta y being here. I'm not going to use that because I'm integrating with respect to x. But think of when we drew pictures like this before. This was like our arc length picture. This is delta s. So in fact, the, what did I call it, width? Yeah, the length was 20, so the width would actually be our delta s. Is the width of our strip. But we can use similar triangles to get an expression for that involving delta x. So think of this triangle that I've drawn right here, this little tiny triangle, would be similar to this big triangle. So this side would be just the width of the pool, which was, or the length of the pool, which is 40. And then the change in depth, so if I'm making this right triangle, really, I'm making the triangle underneath the pool. So this would be the 40. I would just be like making one big rectangle. Here's the hypotenuse, and then what would this side be? Well, if it starts 11 feet below the surface and ends up 4 feet below the surface, then this changes 7. So let's see if I can draw this picture here. So think of the whole pool, and this is the rectangle underneath the pool, right? So this is 7. The change in the depth from the deep end to the shallow end is 7, and the length of the pool was 40. So we can easily figure this side out just using the Pythagorean theorem. So the hypotenuse is just the square root of 40 squared plus 7 squared. So that's 1600, and this is 49, so it'd just be 1649. Well, that may or may not simplify. I'm not going to worry about that right now. And so then we can set up a ratio from this little tiny triangle to the big one. So delta s over delta x is in the same ratio as, so that was hypotenuse over the horizontal side. It's going to be the same ratio as this. Hypotenuse, 1649 over the horizontal side, which is 40. And then to solve for delta s, which was the width of the strip, we'll just multiply both sides by delta x. And so now we have everything we need in our force equation. Okay, and so we're ready to set up the integral to find the total force. Okay, so I'll bring all three of these constants out in front, and we can actually cancel the 20 into the 42 times. So the total force would end up being 62.5 times the square root of 1649 all over 2. There's a decimal place right there. Times the integral of this. I'm going to write it as 11 minus 7 over 40x dx. And our x's were going from 0 to 40 because this was x equals 0 and that was x equals 40. We also use that right here. So we get okay, so the antiderivative is just 11x minus 7 over 40 times 1/2 would be 7 over 80 x squared, and this is going from 0 to 40. I'm not going to round off until the end. Well, you could do the 2 into it. I guess that would be fine. So plug in the 40. 11 times 40 is 440 minus 7 over 80, and 40 squared is 1600 minus, both times we plug in 0, we get 0. And you could just do this straight on your calculator, but I was thinking, okay, so 8, we can cancel a 0 from each of those, and then 8 goes into 160 20 times, and oops, I wrote 400 anyway, so 440 minus 7 times 20 is 140, that would give us 300. And then 2 goes into 300 150 times. So now it's just 62.5 times the square root times 150. And I get about 380,699, and that would be pounds. Let's check that. So 380,699. Okay. Okay. So for part C, estimate the hydrostatic force on one of the sides. So let me draw the side and come back. Okay. So when you do the force on one of the sides, so a side looks like this. Here's where it's at the deep end, and here's where it's at the shallow end. You're actually going to want to break it into 2 parts. So you'll want to do, oops, I want that to be straight across. Because in the bottom part of the pool, if you draw a typical strip, the lengths are changing. The strips are getting longer. But in this little top part, they always have the same length. So let's see, in our pool, oops, this is 40 feet. And then if it's, this whole side is 11, and this side, well, that's only 4, so 4 feet. So you can do the top piece here. So I'm going to think of this as y equals 0. And I'm going to think of this as y equals 11. So when you do the top part, okay, so force is ma, but we've already seen mass was rho v over g, a is g, they cancel. And so rho is 62.5, and then the volume of water pressing down on a strip, so think of the strip, so we'd have length times width times height. The height of the column of water is the same as the depth of the strip, so length times width times the height or the depth of the strip. The height of water is equal to the depth of the strip. Okay, so if I just draw a typical strip in the top part, like say right there. Sorry. So 62.5. So the length would always be 40 feet in that top part. The width would just be the delta y. And the depth, is surface minus y. And the surface is 11. So, and then your y's for this part, so the force on that strip in the top, your y's just go from, well, if this is 4 down from 11, so your y's go, this right here is y equals 7. So when you set up your integral, your y's will just go from 7 to 11. And so now let's look at the bottom. Okay, so if I draw a typical strip in the bottom part. So we still have the same formula for the force exerted on that strip. It would be 62.5. But now the lengths aren't always 40, right? The lengths are changing. At the bottom, it's really narrow, and as it moves up, it gets longer. So we'll leave some space for that. The width would still just be delta y. And the depth would still be 11 minus y, surface minus y. So now we have to get a formula for length. And the formula we used in part D does not work, because I don't know if I still have that up here. It was like y equals 11 minus. So say we switch places with the x and y, and we get 7 over 40 x equals 11 minus y, and then multiply both sides by 40 over 7. This doesn't work, because think, when you plug in y equals 0, which is at the bottom, the length of the strip is 0. So when our y gets bigger, the lengths of the strip should get longer, but if we're subtracting y, that's going to make it shorter. So we can't use the same equation as we did in part D. So let's think of it a different way. So we want the length, and this is how it was even written as the notes, to be a function of y. So the length is L of y. Well, we know what I just mentioned is that when y equals 0, I think that's way at the bottom of the pool. There's no length to that strip. So when y equals 0, L equals 0. And once we get up to y equals 7, now I've reached this point where the length is 40. And so I can find the slope of that line. So 40 minus 0 over 7 minus 0. So 40 over 7. And if it goes through the point 0, 0, that means B is 0. So L equals 40 over 7 times y. And now just think of when you plug in y equals 0, the length is 0. When you plug in y equals 7, the length is 40, which is exactly what we want. So that's all we needed. So the L is 40 over 7 times y, and that was the force on a typical strip. And so the total force is just the integral. So we can bring out all of the constants. Well, I guess that's just 62.5 times 40 over 7. And then our integral will still have a y, and 11 minus y. The delta y becomes dy, and now we have to say the limits on our integral. Well, we're starting at y equals 0 and only going up to y equals 7, because after y equals 7, then the length is always 40. Okay, so you just have to evaluate this integral and then add the two forces together. The answer you get from the bottom plus the answer you get from the top will be the total force on one of the sides.